Hi, today we will talk about
Fractals.
but what are fractals? Let's start with an
Equilateral triangle.
and we will add equilateral triangles on the middle of each side, and we will continue to repeat this process on the added equilateral triangles. This shape is called the Koch snowflake. Whenever I zoom into one of the sides, you'll see the same pattern over and over. This never-ending pattern is called fractals. Every time we add a triangle, the side of the triangle will become 4. Repeating this an infinite number of times will give us infinite sides. Doing this will give the fractal an infinite perimeter. However, the area of the fractal would not be infinite. As you can see, no matter how many times we add sides to the fractal, it would still fit inside the circle. Therefore, the perimeter of the fractal is infinite, but the area is finite. In the 1990s, a radio astronomer named Nathan Cohen was able to apply fractals to antennas. Since Cohen's landlord at the time did not allow their tenants to have antennas on the roof, Cohen decided to make an antenna that was more compact and unnoticeable. To his surprise, his antenna worked better than regular ones. So here's how antennas work. The average antenna is made to receive just one kind of signal. They work more efficiently if the length of the antenna is a multiple of the signal's wavelength. With that said, FM antennas can only receive FM radio signals. TV antennas only receive TV channels, so on and so forth. Fractal antennas are built different. As the fractal repeats its pattern more and more, it can receive many more kinds of signals, and is not just limited to one kind. Because the perimeter of fractals grow quicker than its area, the fractal antenna is not as big as other antennas, only taking a portion of the space. Cohen wanted to design a new kind of antenna that also incorporated fractals, and he did. It's called the Manger Sponge. This fractal is like a 3D version of the snowflake, where it has infinite surface area but finite volume. How do we make the Manger Sponge? First, we begin with a cube. We will divide each side of the cube into 9 sections, just like a Rubik's Cube. Then we remove the small cube in the center of the bigger cube. We will continue to repeat these steps on the rest of the smaller cubes infinitely. The Manger Sponge is widely used in the antennas of cellular phones. It is able to receive all sorts of different signals while taking up only small portions of space. These antennas might be very beneficial, but they also have their downsides. Because they are so small and complicated, they are harder to make and cost more. And even though they are able to receive all sorts of different signals, they can't receive them as well as an antenna that was specifically made for that type of signal. Now you know what fractals are, but what about its
History.
The history of fractals traces back all the way to the 17th century, where a German mathematician and philosopher named Gottfried Leibniz pondered about recursive self-similarity. Although at the time he thought only the straight line was self-similar. He used the term fractal exponents, but gave up as he thought these exponents have not yet been discovered by geometry. After 2 centuries, a German mathematician named Karl Weierstrass presented the first function with a graph that would today be considered as a fractal. The graph had the property of being non-intuitively continuous but nowhere differentiable. Fast forward to the 1960s. A mathematician by the name of Benoit Mandelbrot uses hundreds of years of mathematical concepts and development into coining the word fractal. Mandelbrot used the term fractal as it derived from the Latin word fractus, broken or shattered glass. He expanded the idea of fractals with new innovations, which brought fractals into mainstream mathematics. He uses computers to create visualizations of fractals. One of these fractals is the famous Mandelbrot set.